to study functions that changes abruptly, suddenly at specific times, we use unit step function, or also called as Heaviside's unit function. Okay, as per this, f of t minus a is equal to 0. Its value will always be 0 or 1. It will be 0 when t is less than a, and it will always be 1 when t is greater than or equal to. Now, just think of it. When a is equal to 0, so when a is equal to 0, this function would become f of t is equal to 0 when t is less than 0, and 1 when t is greater than or equal to 0, right? Now what we want to do is we want to find the Laplace of this unit function, not this one where a is equal to 0, but in general f of t minus a. So we want to find the Laplace of f of t minus a. So let's begin. Let's apply the integral. So 0 to infinity of e to the power of minus st f of t minus a dt. Again, since it is a unit step function, remember our previous session, we can split this integral into two parts. What are they? 0 to a st f of t minus a dt plus from a to infinity e to the power of minus st f of t minus a dt. Now remember, here in this case what happens? When we say 0 to a, it means remember it is less than a, right? So when it is less than a, its value is going to be 0. So that means this is 0. That means the whole thing is 0. And here it is 1, right? F of t minus a is equal to 1. For the moment, let's carry it as it is. So integral of a to infinity of e to the power of minus st f of t minus a dt. Okay, now in this step what we'll do is we will say e to the power of minus st. Remember, when it is greater than or equal to a, it is 1 times dt. So integral of, and this we can ignore now. Now integral of e to the power of minus st is what? Minus 1 by s e to the power of minus s t, and the boundary is a to infinity. Let's do the substitutions. Minus 1 by s, remember this becomes infinity, it goes to the denominator, so it becomes 1 by infinity, which is 0. So this is 0 minus, now we are substituting a, so minus 1 by s e to the power of minus s a, and this becomes minus into minus plus 1 by s e to the power of minus s a. Or we could just say e to the power of minus s a by s when we want to find the Laplace of a unit function f of t minus a. Remember, this is a unit function. Okay. Now, in case a is equal to 0, so when a equal to 0, then what happens? Laplace of f of t minus a becomes f of t is equal to e to the power of minus s 0 by s, which is e to the power of 0, which is 1 by s, right? So this is when a is 0. You know, in case of unit functions, it's difficult to figure out the Laplace using our previous methods. So that is where this particular aspect comes into picture. So let us say f of t is equal to, and this is a step function, so 2t when t is less than 5 and 0. between 0 and pi, and it is 1 when t is greater than pi. Okay, let's say greater than or equal to pi. Now what we need to do, remember we only know the step function, that is t minus a kind of setup is what we are familiar with. So what we need to do is we need to convert that into those terms, right, in terms of t minus something. So first of all we have to express in terms of unit function and then find Laplace. Okay, now just use another letter. We are thinking of a different function, g of whatever is the variable here, t minus whatever is the boundary here. So t minus pi is equal to 0 because we are talking of unit function for t less than pi. Okay, and use the same thing is equal to 1 for t greater than or equal to pi. So we have arrived at this. Now we have to write this function f of t in terms of g of t minus pi, and this is the trickiest part. So f of t, so first of all let's rewrite this, right, in a different form. F of t is equal to 2t, right, but this doesn't address both the cases, right? So what I'll do is I'll say minus 2t g of t minus pi. Now does this really work? Say for example, when t is less than pi, right? When t is less than pi, g of t minus pi is 0. So that means 0. That means 2t times 0 is 0, and we are left with 2t. So when it is less than pi, it is 2t. But it doesn't satisfy the second condition. When pi is greater than or equal to, sorry, when t is greater than or equal to pi, g is 1. So 1 times 2t is 2t. 2t minus 2t is 0. But here it's supposed to be 1. So what we'll do is we'll add 1. But that will spoil the first. So if we go back to this, when it is less than pi, then what happens? This is 0. This whole thing is 0. Now we are left with 2t minus plus 1. We want this also to become 0. So what we'll do is we will multiply it with g of t minus pi. So now let's revisit. When t is less than pi, what happens? G of t minus pi is equal to 0, right? This one. So this is 0, this is 0. We are left with f of t equal to 2t, which is perfectly fine. Now, when t is greater than or equal to pi, g of t minus pi equal to 1. This one. So what happens to f of t? F of t becomes g of t minus pi is equal to 1. So 1 times 1 is 1. This is 1. So 2t minus 2t is 0. So let's say 2t minus 2t times 1 plus 1. So 2t minus 2t plus 1. These two gets cancelled out and we are left with 1. So which is what we wanted, right? So you have to arrive at this, in such a way that your original function is satisfied. So basically what have we achieved? We have achieved this. We have got a function g of t minus pi, which we have incorporated, right? So let's into f of t. So f of t is equal to 2t minus 2t g of t minus pi plus 1 time g of t minus pi. Now 2t minus here g t minus pi, g t minus pi is common. So g of t minus pi, let's keep it plus, and minus 2t plus 1. So we have got this. Now we don't want this t to be alone. We want it in terms of t minus pi itself. So how do we do that? So let's take minus 2t plus 1. Now what is our objective? We need to be very clear about that. We want it in terms of t minus pi, right? We don't want t to be alone. Okay. So what do we do? Let's see. Minus 2t plus 1 is equal to minus 2. Let's take it out. So t, because this is plus here, this will be minus, and here we write pi. So basically we write whatever is that what we require. So what we have ended up with is minus 2t plus 2 pi, right? So plus 2 pi is additional. So that means we have to neutralize it. So minus 2 pi. And we don't have 1. We don't have this 1. So what do? We add it. So this minus 2t, we have, replaced it with this. Plus 1 remains as it is. You can expand it. Minus 2t is as it is. Plus 2 pi minus 2 pi becomes 0. So we are still left with minus 2t plus 1. But now we have written it in this form. So now that we have this, let's substitute it. Plus g of t minus pi. And here, what we'll do is this whole thing will be replaced with this. So minus 2 t minus pi minus 2 pi plus 1. 2t. Now let's distribute this g of t minus pi. So minus 2 t minus pi times g of t minus pi, and now minus into plus minus. But since you are opening the bracket, you need to be careful. What we can do is take this into a bracket, in which case remember this will become minus. So 2 pi minus 1 it will become. So now it becomes easier. We can write 2 pi minus 1 g of t minus pi. Carefully look at it. Be clear. Okay. Now see, have we arrived at a situation where we know the Laplace transform? Now we know the Laplace transform of t. Second shifting property tells us what the Laplace transform is. Second shifting property tells us what the Laplace form is. Okay, so Laplace of f of t. So what we are going to do is take the Laplace of both the sides. Laplace of 2t, or what we can do is take 2 out, minus 2 times Laplace of t minus pi times g of t minus pi, minus, again 2 pi minus 1 is constant. So Laplace of g of t minus pi. Now what we can do is we can say 1 times this. 1 itself we can treat it as a function. Okay. So what is the Laplace of t? That is nothing but s square minus 2 times Laplace of 2 minus pi g of t minus pi. That's the second shifting property. So that would be 2 by s square e to the power of minus pi s. Okay. Then minus, what about this? 2 pi minus 1 as it is, and Laplace of this would be 1 by s e to the power of minus pi s. Again, second shifting property. Now here e pi s is common. So 2 by s square as it is. Let's do one thing. Let's make this plus and make this minus and make this plus. Since this is plus, let's make this plus, and let's take e to the power of minus pi s common out. Since this is plus, let's write this first. We can write this as 1 minus 2 pi by s square minus, now this part, 2 by s. Now this is not square, this is s. Okay, 2 by s square. Now let's take s also common, plus e to the power of minus pi s by s square. We can leave it at this point itself, but since I've started it, let's finish it. Now here there is only one s, so let's take one s to the top. It is true. So that is the Laplace transform of the given function. So this type of function, if you get, you will have to use this method to solve it. And as you might have noticed, there are two tricky points here. One is writing the given function in terms of a unit function, and that unit function you have to figure out using the boundaries, rewrite them, and then make sure that everything gets written in terms of that unit step, and then it becomes easy using the second shifting property. Let's do one more just to make sure that we are clear about what is happening. So f of t is equal to t square when t is between 0 to 2 and 6 when t is greater than 2. Now we have to pick a unit function. Pick a unit function. Now how do we pick it? Take any function g. See, ultimately it's just a different letter other than f. T minus whatever is the boundary. So t minus 2. And we want it to be a unit function, so it is going to be 0 and 1. And this would be true when t is less than 2. Similarly, t minus 2 is equal to 1 when t is greater than 2. Right? Okay, now we have to write this function f of t in terms of g of t. So f of t is equal to t square as it is. Now we have to keep adding and subtracting expressions, terms to satisfy f of t. So minus t square times g of t minus 2. Okay. Now when it is less than 2, this term will become 0. We will be left with t square, which is what we require. But then what happens is when it is greater than 2, it should be 6, right? So that means this should become 1. So when it becomes 1, t square minus t square will disappear and we require 6. But then because this 6 is there, the first condition gets spoiled, right? So when it is less than 2, this becomes 0, this whole thing becomes 0. So t square minus 0 plus 6. So it becomes t square plus 6. But we want only t square. So what we do is we multiply it with g of t minus 2 as well. So in which case what happens? This also becomes 0 and this also becomes 0. So let me write it very quickly. When t is less than 2, g of t minus 2 equal to 0. So f of t becomes what? T square minus, remember this becomes 0. So this whole thing is 0. This is 0. So this also becomes 0. So which is t square. Now when t is greater than or equal to 2, then g of t minus 2 equal to 1. So in that case, f of t becomes t square minus t square times 1 plus 6 times 1, right? So which means this disappears and we are left with 6, which is exactly what we wanted. So that means this f of t written in terms of t minus 2 is perfect. So let me rewrite it. F of t is equal to t square minus t square g of t minus 2 plus 6 times g of t minus 2. Okay, t square minus g of t minus 2 is common. Let's make this as plus minus t square plus 6. Now this also should be in terms of t minus 2. So let's take minus t square plus 6. Now, one of the ways of getting t minus 2 is having a perfect square of t minus 2. Right? So write the perfect square or just square this and write it. So this becomes 2 square minus 4t plus 4. So what happens now? What do we have extra? We have minus 4t plus 4 multiplied by minus. So that means 4t we have additional. So we write minus 4t so that it gets neutralized. And we have minus 4. So minus 4 is we add plus 4 to neutralize it. And then we also have plus 6. So this becomes minus. Now this becomes t minus 2 square minus 4. This also should be in terms of t minus 2. So 4 t minus 2 plus 10. Okay. But remember, uh, I have written t minus 2. So extra what I have got now? Minus 4 times minus 2, that is plus 8. But here I have minus 4. So 8 extra I have added. So I have to subtract minus 8. I have to subtract 8 to neutralize that. So minus t minus 2 square minus 4 times t minus 2, and I'm left with plus 2. Looks complicated, but if you think about it, you will get used to it if you solve a few questions. Now let's incorporate this in your main. So t square plus g of t minus 2 times, we substitute this with this, minus t minus 2 square minus 4 times t minus 2 plus 2. And now let's open up the bracket. So t square plus, no, minus t minus 2 square g of t minus 2 minus 4 times t minus 2 g of t minus 2 plus 2 times g of t minus 2. And now we know the Laplace transform of all of these. So Laplace of f of t is equal to Laplace of t square is this t? Yes, this will be 2 by s cube. This would be applying the second shifting property, right? So second shifting property, e to the power of minus 2s by s cube minus 4 times, again second shifting property, this would be s square times e to the power of minus 2s. Then we have plus this one. We can treat this as 1 times g of t minus 2. So 2 by s e to the power of minus 2s. Okay, this would be 2 times. Okay, we should not miss that. Is equal to, now 2 by s cube minus e to the power of minus 2s is common. And let's take s cube also common out. So what are we left with? 2. Similarly, this is minus. So this would be, let's take this minus inside. So let this be plus. Let this be minus. Minus 4s. And this will be plus 2s square. Because s cube is taken out. So s square, s cube will cancel and we'll be left with s. Okay. So now let's rearrange this to make it e to the power of minus 2s by s cube 2s square minus 4s minus 2. So that is the Laplace of the given function, this one. Okay, so that's it.